Hey everyone. Uh I'm gonna update you on what I've learned about quantum mechanics and its mathematics. Essentially, I've learned it from the book called The Mathematics of Quantum Mechanics. I've learned from the first two chapters again, which is called Complex Numbers and Linear Algebra. First chapter is, of course, complex numbers. It starts with a problem. Normal numbers can't give you a square root of a negative number. So, as human does, we invent one, which is called I, defined as a square root of -1. Once you have that, a complex number is just a pair of real numbers stuck together, a real part and imaginary part, written as plus b times y, a plus b times y. From there, the chapter covers the basic arithmetic, adding, subtracting, and multiplying complex numbers, which works a lot like regular algebra, just remembering that I squared equal -1. Then it introduces two key tools: the complex conjugate, which flip the sign of the imaginary part, and the modulus, basically the size or the length of the complex number, found by multiplying a number by its own conjugate and taking the square root. The big finale of the chapter, not the big finale, just the last part of the chapter, which includes the Euler's formula. E to the I theta equals cosine theta plus I sine theta. It connects complex number to circles and rotation, lets you write any complex number in polar form as a length and an angle instead of two coordinates. It helps to describe the way quantum rotates and phase shifts, and polar form is a natural way to describe that. Secondly, the second chapter is linear algebra. It starts with vectors with columns and numbers, then I got to matrices with grids of numbers that act on vectors. We cover the basic operations, just vector addition, scalar multiplication, and matrix of multiplication. Then it gets to more specific, like transpose, which flips rows and columns, complex conjugate, which applies the same principles, is from chapter 1 to conjugate to every entry, and the conjugate transpose, which do both at once. From there, I learned about the inner product, a way of multiplying two vectors together to get a single number, and the norm, which is the inner products of way of measuring a vector's length. This connects directly back to the modulus from chapter 1. The chapter also introduces basis vectors, the idea that you can build any vector out of a small set of building block directions, and shows that the inner product can be understood geometrically as a projection, measuring how much one vector points along the other. Finally, it touches on the special matrices, including unitary matrices that preserve length when they act on the vector. The property turns out to be exactly what's needed and describe how quantum states evolve without losing probability. Yeah, so by the end of chapter 2, I've got two ingredients from quantum mechanics I can build from: complex numbers to describe phase and rotations, and linear algebra to describe states and how they transform. Next, I will be learning about chapter 3, which will be further into the subject, and it will include computing stuff like qubits, measurements. Yeah, thanks for watching.